Methanol can be used as a fuel. Table 1 gives the bond dissociation energies for the complete combustion of methanol. The balanced equation for the reaction is given to us here. So what information has the examiner given us? They've told us that methanol is a fuel. Now, methanol is a type of alcohol. I can tell that because it has the ol end to its name. And it's a fuel which is a chemical store of energy. Table 1, shown here, gives us the bond dissociation energies. This is the average amount of energy required to break 1 mole of a particular bond. And we're using this to work out what happens with complete combustion of methanol. Now, complete combustion is when you have excess, too much oxygen. And combustion is just the science word for burning, a type of oxidation reaction. Now, we're given the balanced equation, and that's given to us here. Now, hopefully you can see that this isn't the molecular formula. We've been given the displayed formula, so we can see every atom and every bond, and that will make the bond energy calculations a little easier to do. Part A. Explain why activation energy is needed to start the reaction. What's the command word? The command word is explain. The examiner has also used a key phrase, activation energy. That's the minimum energy required to start a reaction. But the question we're being asked is, why do you need the activation energy? And you need it to break the bonds in the reactants. So, part B, list all the bonds that are made in the products. So, what's the command word? The command word is list. And we've got to list all the bonds, these are covalent bonds of course because they're all molecules, that are made in the products. So let's have a little look. Here we've got carbon dioxide, and each carbon dioxide molecule contains 2 C double bond O's, but we're making 2 of them. So that means overall we are going to be making 4 times C double bond O. Please notice I've shown the double bond there, not a single bond. Now let's look at the water. Each water molecule makes 2 H bond O, but we're making 4 water molecules, so that gives us 8 OH bonds, and we get 1 mark for each. Okay, part C. Calculate the energy released when the bonds are made in the products. What's the command word? The command word is calculate. And what are we calculating? We're calculating the energy released when the bonds, once again they're covalent bonds, a shared pair of electrons, in the products. So let's think about the bonds in the carbon dioxide first of all. And remember, we've got 4 lots of C double bond O. So look in the table, C double bond O is 799. So we need to do 4 times 799. And when you pop that into your calculator, you will get an answer of 3196 kilojoules per mole. We've also got, thinking about the water now, we've got 8 lots of OH. So looking at the table, 464. Pop that in your calculator and you will get an answer of 3712. Now that's not the end of the story because of course you make both the carbon dioxide and the water in this reaction. So the overall energy release is actually the sum adding together these 2 numbers. So we're going to write out all of our working just in case we pop something incorrectly in a calculator and you still get the working out marks. So you're going to add 3196 plus 3712 into your calculator and you will get an answer of 6908. Once again, that's kilojoules per mole. Now it doesn't ask you for the units, but I like to give the units if I can. There we go. Part D. 5,616 kilojoules per mole of energy is needed to break the reactant bonds. Use this information and your answer from Part C to calculate the energy change in this reaction. Include a sign in your answer. So what's the command word? Well, that's a trick question. There's actually more than one. The first command word is use, the next one is calculate, and arguably include, because it's telling you to do something, is a command. So we're including something, so that could be considered to be a command word. So what key information have we been given? We've been told that 5,616 kilojoules per mole of energy is needed to break the reactant bonds. So that's the energy that we need to pop in. And we've also been told to use our answer, which I'm just underlining here, from part C. And we need to include the sign in our answer. Now, because this is a combustion reaction, the overall energy change must have a negative value because it has to be exothermic because it is a combustion reaction. Now, the energy that we put in is a positive value because I need to add this energy to break those reactant bonds. But the energy that is released when I make the product will have a negative value because it's been released from the system. And that's our answer in part C. When we pop that into a calculator, we get an answer of minus 1292, and once again, that's in kilojoules per mole. Now you get one mark for doing this sum here, and 1 mark for the overall answer, but don't forget it must have a minus sign.